Cylinder of uniform mass 5 kilograms, radius 3 meters, and length 8 meters is rotated about an axis passing through its center of mass. Part A, derive an expression for its moment of inertia. And part B, using your answer to part A, find the actual value for the moment of inertia. Okay, let's start with part A. So over here above, I have drawn a small little cylinder to represent what we're trying to actually look at. So from the point of the origin to the outside, it has a radius of r, and that r is going to equal to 3. But we're going to come back to the actual values in part B, since it's much harder to work with numerical values instead of using letters to clearly quantify what you're showing. Okay, then it'll have some length, we'll call that length h, and it'll have some mass, we'll call that mass m. We also have some volume, which we'll call v. And we know that the volume is just going to be pi capital R squared times my height. Okay, now how we go around finding the moment of inertia? Well, let's do this. Let's take a small little strip of a hollow cylinder. Let's find the moment of inertia for that, and then we can integrate it to find the moment of inertia for a giant cylinder. Okay, so essentially what I'm saying is we'll take a small little cylinder. Sorry, it's not the best, but look, something like that. Okay, the height or the length of it is going to be exactly the same. However, it's going to be a distance lowercase r away from the origin. Why is this? Well, because we can vary the r, so it will vary between 0 and capital R, so we can get infinite number of possibilities for how big our cylinder will be. And if we can sum those all up, we'll get the moment of inertia for the whole cylinder. It also have some little width of dr, and it'll have some mass dm and some volume dv. Okay, now how will we find out the volume of this? Well, there are two ways. We know that the volume of a prism is cross-section times height. Now, the volume of this prism right here will just be the volume of the outer cylinder minus volume of the inner cylinder. In other words, the volume of this minus the volume of that. Or we can basically imagine this as a sort of sheet, metal sheet. We cut it with somehow, maybe a laser or a scissor, and we just lay it out flat. And then we can find the volume because it'll become basically like a cuboid with length times base times height. Okay, so now let's start off with the cross-section method and then use the cutting method with the cutting with the laser and the metal sheet just to cross-check our method. Okay, so the volume of this, which we'll call dV, will equal to the volume of the outer cylinder, which is pi times the height times the radius squared, which is r plus dr whole squared, minus pi h r squared, because that's the inner and smaller cylinder. So what is dV? Well, let's FOIL and expand out the bracket. It'll be pi h. Actually, I'll factor out pi h. Be r plus dr whole squared minus r squared. Okay, now let's FOIL pi h. So it's basically r squared plus 2r dr plus dr squared minus r squared. And as we can see here, we can cut out the r squareds. And let's think about what the drs will go to, because we can't have a dr squared, right? But as we tend dr closer and closer and closer to 0, dr squared becomes 0 much, much, much more faster. So in other words, it's basically negligible. So we can cut this out. My bad, I moved it a bit. That's too much. Okay, we can cut that out here. And I get that dV is going to be equal to pi h 2r dr, or if that looks neat, I guess 2 pi rh dr. Now, if you don't really understand this method, we can use the other method, which might make a little bit more sense. It's a bit more intuitive to cross-check. Let's say we were to get a little sliced cut through the cylinder, straight through the middle, or like through an axis, straight line. Then we unfold it. Well, it'll look something like a cuboid. So here, here, here. Okay. Now the thickness of this cuboid is going to be thickness dr. So I can write that here, dr, dr, dr. And now the sides, well, first side is going to be h, that goes this side. The second side is going to be the circumference of the smaller circle, which is just 2 pi r. So I can say that this is 2 pi r, and this is h. So volume is basically 2 pi r times h times dr, or my dv is going to equal to 2 pi r h dr, as seen over here. We both get the same answers. As long as, if you can understand both, that's great. If you can understand one of them, that's also great. But if you understand none of them, that's not great. Now then, this also has a small little mass, dm. Now, what's a way where we can link a dm and dv? Well, if we look at the ratio of mass to volume, in other words, the volume density, we know that the volume across any little point, whether that be a giant cylinder like the one we were supposed to find out, or whether that be this infinitesimally small strip, the density is going to be the same since it's a ratio of the mass to volume. Or, well, in this case, at least because it has uniform mass. So I can say that the density, which is given by the Greek symbol rho, is going to equal to mass over volume, which is also equal to dm over dv. Now then, if we multiply dv by both sides, we get that the dm is equal to rho dv, which is equal to m over v dv. Okay, now what is v? Well, v is just going to equal to pi capital R squared h. And what is dv? Well, we just found out what dv was. That was 2 pi rh dr. Now, some pretty nice canceling out here. We can cancel out the pi's. We can cancel out the h. So you get that dm is equal to 2mr dr over capital R squared. Now, this is great because we can actually figure out the moment of inertia from this expression. Let's remind ourselves what the formula for moment of inertia is. I, moment of inertia, is equal to the integral of r squared dm, where r is this little variable r that we have seen over here. Now, because dm, now r and dm are actually related to one another, there was no way we could actually bring r squared out of the integral. So dm, our expression for dm over here, has actually fixed that. And now it's actually fairly simple to find the moment of inertia, as you'll see. So let's plug in the value for dm. dm, as we saw, was 2mr dr over capital R squared. Now let's also find out our limits of integration. Well, what's the smallest value r can be? Well, looking from the cylinder, r can't be negative because that's just going in the other direction, isn't it? And so basically, the smallest value can be is just 0 right at the center over here. And what's the largest value can be? Well, the maximum value r can possibly be is, well, capital R. So I could say that my limits of integration is from 0 to capital R. Or since this actually, I can group up the r squares and 2m over r squared is a constant, I can say that my moment of inertia is 2m over r squared times the integral from 0 to capital R of r cubed dr. Now, as you can see, it's a fairly simple integral. Well, I can integrate r cubed dr. That's going to be giving me r fourth over 4. So I will equal to 2m over r squared times r to the 4 over 4. From r is equal to 0 to r is equal to capital R. Now, let's think about this. When we put 0 into this integral, or this value, it's a constant times 0. And what's that? That's just 0. So I can essentially just cut that out. Now, what about r? Well, r will actually give us a value. So if we substitute that in, we get 2m times r to the 4th over r squared times 4. And again, there's some pretty nice canceling out over here. R to the 4 over r squared, that's just r to the 2nd. And 2 over 4, that's just half. So I finally, I'll actually write this on a different line. My moment of inertia, is equal to half m r squared. And you may see this, seen this before because this is actually the moment of inertia for any cylinder of uniform mass. And you'll also see this in many textbooks as well. And that is the formula we're going to be using in part B. So part A is checked. Now part B, find out the actual moment of inertia using the values that we are given. Now we're given that the mass is 5 kilograms, radius is 3, and length is 8. However, as seen before, since the lengths are canceled out and are working out, that's not really going to matter. So the only one we're really focused on is the mass 5 kilograms and the radius 3 kilograms. So now let's plug that in to part B. So moment of inertia I is equal to half mr squared. So moment of inertia is half times our mass, which is 5 kilograms, times of radius, which was 3 meters squared. So our moment of inertia will equal to half times 5 times 9, and the units will be kilograms meters squared. So finally, our moment of inertia for this cylinder was half times 5 times 9, 45 over 2. And I'll just leave it as a fraction. Kilograms meters squared. That is our answer. So why was I looking at this problem? Well, because moment of inertia is one of those very important concepts. It's very useful when we're trying to spin stuff in physics. We're trying to basically maybe have a pulley, and maybe this pulley rotates when we're trying to lift stuff up because it basically does less effort to help us. So it actually saves lots of time and energy. Just given an example here, maybe this would rotate and it'll just be a lot more easier to lift up objects every day. And that's like, especially for cylinders, that's mainly what it's used for. So that I felt that this would be a good example to see how we can tie in moment of inertia and real world physics together. So I think it was a pretty neat problem. And if you want to see more like this, please let me know.